Welcome to this comprehensive Pytorch tutorial on BatchNorm versus LayerNorm. Today, we're diving into two crucial normalization techniques that are fundamental for training deep neural networks. Normalization techniques help us achieve faster convergence by stabilizing gradients during training, allow us to use higher learning rates for more aggressive optimization, and reduce sensitivity to initialization and hyperparameters. In this tutorial, we'll explore batch normalization, which normalizes across the batch dimension, and layer normalization, which normalizes across the feature dimension. Most importantly, we'll understand why LayerNorm has become more popular in recent architectures like transformers. Let's start by importing the required libraries and setting up our environment. We'll need Pytorch for our neural network operations, NumPy for numerical computations, and Matplotlib and Seaborn for visualizations. I'm also setting random seeds to ensure our results are reproducible. Great, we're running Pytorch version 2.5.1. Our environment is all set up for exploring normalization techniques. Now let's dive into part 1, batch normalization. The mathematical foundation of BatchNorm uses a simple but powerful formula. We normalize inputs by subtracting the mean and dividing by the standard deviation, then apply learnable scale and shift parameters gamma and beta. The key characteristic here is that the mean and variance are computed across the batch dimension for each feature independently. BatchNorm maintains running statistics during training and, importantly, behaves differently during training versus evaluation. Let's see BatchNorm 1D in action. I'm creating sample data with 32 samples and 100 features. We'll initialize a BatchNorm 1D layer and apply normalization to see how it transforms our data. Notice how BatchNorm normalizes each feature across the batch dimension independently. Perfect. As you can see, our input had a mean close to 0 and standard deviation close to 1, but wasn't perfectly normalized. After BatchNorm, the output has a mean of exactly 0 and standard deviation of 1.0002. When we look at individual features, each one has been normalized to have 0 mean and unit standard deviation across the batch. This is the essence of batch normalization, normalizing each feature independently using batch statistics. Now let's look at BatchNorm 2D, which is commonly used in convolutional neural networks. Here we're working with image data that has batch size, channels, height, and width dimensions. BatchNorm 2D normalizes each channel independently, computing statistics across the batch, height, and width dimensions. Excellent. We can see that BatchNorm 2D successfully normalizes each channel. The per-channel mean is essentially 0, and the per-channel standard deviation is exactly 1. This is crucial for CNNs, where each channel might represent different features that need independent normalization. Let's visualize how BatchNorm actually transforms distributions. I'm creating 3 features with deliberately different means and variances to show how BatchNorm brings them all to the same scale. Feature 1 has high mean and low variance, Feature 2 has negative mean and high variance, and Feature 3 is already normalized. This visualization beautifully demonstrates the power of BatchNorm. Look at the image showing before and after BatchNorm. Initially, our 3 features had completely different distributions, scattered across different ranges. After BatchNorm, all 3 features are perfectly aligned with 0 mean and unit variance. The assertions confirm that BatchNorm successfully normalized all features to have mean approximately equal to 0 and standard deviation approximately equal to 1. Now let's move to part 2, layer normalization. LayerNorm uses the same mathematical formula as BatchNorm, but computes statistics completely differently. Instead of normalizing across the batch, LayerNorm computes mean and variance across the feature dimensions for each sample independently. This means each sample in the batch gets its own normalization, with no dependency on other samples. Let's demonstrate LayerNorm with a typical use case in transformers. We'll create data representing a batch of sequences with embeddings. Here we have 4 samples, each with 10 sequence positions and 512 dimensional embeddings. LayerNorm will normalize across the embedding dimension for each position independently. Perfect. LayerNorm has normalized each position independently. Looking at a single position, we get exactly 0 mean and standard deviation of 1.001. When we check all positions, they all have the same normalized statistics. This independence from other samples is what makes LayerNorm so powerful for sequence modeling. LayerNorm can also be used with images, though it's less common than in sequence models. Here we're normalizing over the channels, height, and width dimensions for each image in the batch independently. As expected, each image in the batch is normalized independently. Every image now has 0 mean and unit standard deviation across all its pixels and channels. This batch independence is a key advantage of LayerNorm. Let's visualize LayerNorm's behavior by creating samples with different distributions. Each sample will have different overall statistics: high mean and low variance for sample 1, low mean and high variance for sample 2, and already normalized for sample 3. This visualization shows how LayerNorm works differently from BatchNorm. Look at the image. Before LayerNorm, each sample had its own distinct distribution. After LayerNorm, each sample is independently normalized to have 0 mean and unit variance. Unlike BatchNorm, which normalizes features, LayerNorm normalizes samples, making it perfect for scenarios where batch statistics aren't reliable or available. Now in part 3, let's explore the key differences between BatchNorm and LayerNorm, starting with a visual comparison of their normalization axes. I'm creating a visualization to show exactly what gets normalized together in BatchNorm versus LayerNorm. The colored groups represent elements that are normalized together. This visualization clearly shows the fundamental difference. Look at the image with 3 panels. The middle panel shows BatchNorm groups, where colors indicate what gets normalized together. BatchNorm normalizes vertically, across the batch dimension for each feature. The right panel shows LayerNorm groups, where each row, representing a sample, gets its own color because it's normalized independently. BatchNorm normalizes across samples, while LayerNorm normalizes across features. Let's examine how training versus evaluation behavior differs between these normalization methods. This is a crucial difference. I'll demonstrate how BatchNorm and LayerNorm behave differently in training versus evaluation mode. BatchNorm uses batch statistics during training, but switches to running statistics during evaluation. This is a critical distinction. BatchNorm shows a significant difference of 0.327 between training and evaluation outputs because it uses different statistics: batch statistics in training versus running statistics in evaluation. LayerNorm, on the other hand, shows exactly 0 difference. It produces identical outputs in both modes because it always computes statistics from the current input, making it more predictable and easier to debug. Another important aspect is batch size sensitivity. Let's test how both normalization methods perform with different batch sizes. I'm testing both normalization methods across a range of batch sizes, from 1 to 128, to see how stable their outputs are. Look at this graph showing normalization stability versus batch size. BatchNorm's performance clearly degrades with small batch sizes, showing unstable standard deviations. LayerNorm maintains perfectly consistent performance regardless of batch size, staying close to the ideal standard deviation of 1. This batch size independence is one of the main reasons LayerNorm has become so popular. In part 4, let's discuss why LayerNorm has become more popular recently. The key reasons include batch independence, working with any batch size including 1, consistent behavior between training and inference, natural fit for sequential models like RNNs and transformers, graceful handling of variable length sequences, and no synchronization needed across GPUs in distributed training. Let me show you a practical example of a transformer block using LayerNorm. This is the standard architecture used in models like BERT and GPT. Notice how LayerNorm is used before both the attention and feed-forward layers in this pre-norm architecture. Excellent! Our transformer block handles all combinations of batch sizes and sequence lengths gracefully. Whether we have a single sample or 16 samples, whether we have 10 tokens or 100 tokens, LayerNorm ensures stable normalization. The output maintains consistent statistics across all configurations. This flexibility is why every modern transformer uses LayerNorm rather than BatchNorm. Let's also compare how CNNs work with BatchNorm versus LayerNorm. I'll create convolutional blocks using both normalization techniques to show their differences. This comparison reveals an important limitation of BatchNorm. With a small batch of size 2, both methods work, though BatchNorm's output standard deviation is slightly less stable. But with a single sample, BatchNorm requires special handling or fails in evaluation mode, while LayerNorm works perfectly with a standard deviation of 0.5842. This is why LayerNorm is preferred for inference scenarios where you might process one image at a time. Part 5 provides practical guidelines for when to use each normalization method. Use BatchNorm for CNNs with fixed batch sizes, traditional computer vision tasks, large batch training with consistent batches, and distributed training when you can synchronize statistics. Use LayerNorm for transformers where it's standard, RNNs and LSTMs for sequential processing, scenarios with variable batch sizes including single sample inference, online learning when processing samples one at a time, and small batch training where it's more stable than BatchNorm. Let me create a comprehensive comparison table that summarizes all the key differences between BatchNorm and LayerNorm. This table provides a complete reference for choosing between BatchNorm and LayerNorm. Key takeaways include BatchNorm normalizes across batch dimension, while LayerNorm normalizes across feature dimension. BatchNorm requires minimum batch size of 2, while LayerNorm works with single samples. BatchNorm behaves differently in training versus evaluation, while LayerNorm is consistent, and BatchNorm requires synchronization in distributed training, while LayerNorm doesn't. Let's conclude with why LayerNorm has become more popular recently. The architecture evolution toward transformers naturally benefits from LayerNorm's properties. Training flexibility is enhanced as it works with any batch size without careful tuning. Inference advantages include single sample processing without special handling. Distributed training is simplified with no cross-GPU synchronization required. And theoretical benefits include more stable gradients and better suitability for attention mechanisms. While BatchNorm remains valuable for CNNs, LayerNorm has become the de facto standard for NLP, transformer-based models, and any architecture requiring batch size flexibility. Finally, here's a quick reference for common usage patterns to help you implement these normalization techniques in your own projects. And there you have it. Remember the key patterns. For CNNs, use BatchNorm to D after convolutions. For transformers, use LayerNorm with your hidden dimensions. For RNNs, apply LayerNorm to hidden states at each time step. And remember, when in doubt, LayerNorm is usually the safer, more flexible choice. Thank you for following along with this comprehensive tutorial on normalization techniques in Pytorch.